Okay, I decided to add another podcast to emphasize why the intensification of the boundary current happens on the west, why the western boundary current is narrow, strong, and deep, whereas the eastern boundary current is broad, shallow, and not so deep, not so fast, not so intensified. When we look at the potential vorticity equation near the surface, we said the boundary forcing or the wind stress forcing creates negative vorticity, and the interior transport generated by the winds is also southward, so you are going from high Coriolis to low Coriolis, so that term is also negative and the other terms are small. Whereas in the boundary current where you have transport from the south to north, the minus r dmy dx term is much greater than 0 to compensate for these mass flux and vorticity flux from the winds into the ocean. And this is the zonal gradient of the meridional transport, and the sign has to be greater than 0. So if you look at the current from the western boundary towards the interior, you get the right sign. If you try to put the boundary current on the eastern side, then the northward transport, which is required to satisfy the wind-driven southward transport, can be satisfied, but you cannot generate positive vorticity to compensate for the negative vorticity put in by the winds. So it doesn't work on the eastern boundary. So that's one way of explaining, that is the way of explaining why the western boundary intensification has to happen on the west. Similarly, when we look at the vorticity generated by the deep water formation, which is creating a transport from north to south, so that is generating decreasing vorticity or negative vorticity because the water is forced to go south. It cannot go north into the northern ocean, northern part of the ocean, so it has to flow south. And the source term, or the deep water formation, is putting vorticity that is greater than 0. So you need to then have the gradient in the zonal direction of the meridional transport to be much less than 0, because you are also moving the water south to north in the interior, where you are generating vorticity because you are going from low F to high F, so you have to compensate for that as well. So again, by that logic, you cannot have strong zonal gradient of the meridional transport on the eastern boundary, so that also requires western boundary intensification. This is all quite mathematical. If you want to do it in a simpler way, typically it is explained this way. So you have western boundary trade winds, westerly winds, which are creating a clockwise gyre or circulation in the northern hemisphere. By the same token, using Coriolis being to the left of the direction of motion, you get a counterclockwise gyre in the southern hemisphere. But focusing here, we have to explain why the boundary current on this side is intensified and why is there a southward transport in the interior. So imagine the Coriolis pushing the water northward here to the right of the direction of motion. So trade winds are pushing the water westward. Coriolis will push the water northward here. Westerlies are pushing the water eastward, so Coriolis will push the water southward. But what is the big difference between this northward and this southward transport? The Coriolis is much lower here, so the term F times U is much smaller here than the term F times U over here, because F increases in this direction. So you have more southward transport here here at a higher F than the northward transport here. So there is a net southward transport created again because of the F varying and the winds changing direction from the trade winds to the westerlies. So you have interior southward transport because of Coriolis, and you curl your fingers around the east trade winds going, so I don't know, you have to do it yourself. Trade winds going towards the west and westerlies going towards the east, and that points your finger into the ocean. So that is negative vorticity. So the winds are putting negative vorticity into the ocean. So you have to create a current which is going to transport the water back northward to compensate for this southward transport induced by the winds and the increasing Coriolis with latitude. And you have to generate a positive vorticity to compensate for the negative vorticity being generated by the ocean. Otherwise the ocean will keep on churning more and more and more. So you have to balance the vorticity also. So the two can be accomplished in this way. So we have the north equatorial current going westward, creating poleward transport, North Atlantic current going eastward, creating southward transport, and it is matched with this Canary current, which is bringing cold water southward. But this current tends to be broad, shallow, and weak, whereas this northward current here tends to be western boundary intensified, and that is what we call the strong inertial boundary current. And why is it intensified over here? You can look at it this way. So the sea level calculations we did would show that if there is convergence of water in the middle, then you're piling up warm water, the thermocline is pushed down, water is piled up, and then water is going to flow down the hill by gravity, and then Coriolis is going to act on that and create these currents. So you see that water is piled up in the middle here. It's an asymmetry because of these issues we talked about, and so gravity is making the water flow down. Coriolis is going to act in the other direction. So you are going to have clockwise currents around this hill of water that's been generated. In fact, if you go from the equator to the middle of the gyre, there's an increase of sea level by almost 2 meters in the North Atlantic. Okay, so that explains the southward transport, piling up of water by convergence in the middle, and we have to now explain why this current is narrow and strong and deep compared to this current on the east. And this is how you can think about it. So here are winds. Like Stommel, we assumed similar profile here. So you can create northward transport to compensate for the interior transport here, or you can also create northward transport here with the interior transport on this side. But what is the difference? Mathematically, both solutions are possible. You have to move water northward to compensate for the interior southward transport, but you also have to generate positive vorticity because we are putting negative vorticity in here. And that can only be done on this side. So if you think about the boundary current here, the velocities have to, the currents have to go to 0 on the boundary and increase to the interior, and they have the positive vorticity sign on this side, whereas if the northward flow was on this side, then the vorticity, if you put a paddle in here, it's going to be rotating in this direction and not in this direction. So you generate more negative vorticity if the boundary current is intensified on this side. So you can conserve mass here, but you cannot conserve vorticity here. Only on this side you can conserve mass and vorticity. Okay, so you can try other combinations and basically convince yourself that western boundary intensification happens because you have interior flow that is southward, and the boundary current is going to be intensified and match the interior flow like this. So near the inertial boundary current is going to produce positive vorticity and northward transport only on the western boundary. The same arguments also work in the southern hemisphere when you just switch the sign of the Coriolis. Okay, so this is an easier way to understand. If you have intensification on the eastern boundary, you're going to end up with more negative relative vorticity, whereas the wind is already putting in negative vorticity, so you will not conserve vorticity, you will just churn the ocean more. So that's another way to think of why western boundary intensification happens on the why the western boundary current is intensified as opposed to the eastern boundary current. And when you run an ocean model, you don't have to run a coupled model. You can run an ocean model with full equations of motion that we looked at, and the winds are often prescribed from either satellites, from ship observations, or from reanalysis products that we talked about. And in that case, you don't have to worry about vorticity and making assumptions about isopycnals and this and that. The full model will take the wind forcing, momentum, penetration into the ocean, also the heat fluxes and the freshwater fluxes and everything, or you can do it just with the wind forcing, and it will automatically generate the western boundary intensification as long as you are on a beta plane and if you allow Coriolis effect to change with latitude. Okay, so in the real model, full model, you don't have to do any simplifications. It will produce a western boundary intensification. Of course, there are other details. Why does the western boundary separate where it does, and whether models can do that, and so on and so forth, but let's not worry about that right now. So this is kind of the wind-driven large-scale ocean circulation. We obviously didn't do much on the thermohaline circulation here. But you can imagine that even in a fully forced, fully coupled ocean atmosphere model, you just give it radiation forcing at the top of the atmosphere, and the ocean atmosphere system will take that energy, distribute it properly. It will produce winds, equator to pole temperature gradients. It will produce ocean currents and western boundary intensification, deep water formation, deep western boundary current, and so on. It won't be perfect because models have some parameterizations, as we said before, mixing in the ocean, for example, or eddy diffusivity, eddy viscosity. All these terms are not always precisely modeled or prescribed, so there are always some uncertainties, biases, and so on in the model. But it's amazing that given the forcing at the top of the atmosphere, they can produce all the features: winds, trade winds, westerlies, ocean currents, monsoons, ITCZ, El Niños, and so on and so forth. Okay, let us leave this chapter here and then move to large-scale atmospheric circulation in the next chapter. Okay.